Welcome to Pratham Science Academy classes, and we are about to start with set 1. So, this is set 1 of 2023. So, for set 1, it is subset 1 because in each set there are three subsets. So, let's move on to the first question for physics. It gives us that four identical resistors of resistance 8 ohm are first connected in series so as to give an effective resistance Rs, and then they are connected in parallel, and their effective resistance is called Rp. Then what is the ratio of Rs by Rp? Resistance in series to resistance in parallel. We have to find the ratio. So these are four identical resistors of 8 ohm each, and when they are connected in series, we know how to connect the resistors in series. They are connected end to end. So this is how they are connected in series. The resistors are connected end to end. And these are four identical resistors. So this is second one. This is the third one. And this is the fourth one. Okay, so these are four identical resistors of 8 ohm each. And they are connected in series first. And we know that their effective resistance, that is the net resistance of this series, is it's given by R1 plus we have to add each of the individual resistors resistance. So this will be 8 plus 8 plus 8, that is equal to 32 ohm. Okay, this resistors was when the resistors were connected in series. अब इन्हें कनेक्ट किया गया है पैरेलल में. So we know how to connect them in parallel. इन सभी रेजिस्टर्स का एक एंड बैटरी के एक एंड के साथ और सभी रेजिस्टर्स का दूसरा एंड बैटरी के दूसरे एंड के साथ कनेक्ट करेंगे तो हम कहेंगे ये सभी पैरेलल में, they are connected in parallel. So these are identical resistors, four identical resistors of 8 ohm each, and this is how we have to take one end of all the resistors and connect them to one end of the battery. Let's say this is a battery, and one end of all the resistors they are connected to other end of the battery. That's when we say that they are connected in parallel. और हमें पता है resistance in parallel इस पूरी जो कॉम्बिनेशन है रेजिस्टर्स की पैरेलल में, इसकी जो इफेक्टिव रेजिस्टेंस है पैरेलल में, उसका रेसिप्रोकल जो है वो सम ऑफ रेसिप्रोकल ऑफ इंडिविजुअल रेजिस्टेंसेस होता है, 1/R2 प्लस 1/R3 प्लस 1/R4. तो ये हो जाएगा 1/8 प्लस 1/8 प्लस 1/8 प्लस 1/8, which is 4/8, that's equal to 1/2. But this is not the resistance, this is the reciprocal of the resistance. और इसका रेसिप्रोकल करने पे हमें मिल जाएगी पैरेलल रेजिस्टेंस की इफेक्टिव रेजिस्टेंस. तो ये है 2 ओम और हमसे पूछा है इनका रेशियो RS by RP. So resistance in series is 32 ohm and resistance in parallel is 2 ohm. So this is 32 divided by 2. 32 divided by 2, that is equal to 16 ohm. So our answer is option D, which is 16 ohm. Okay, for question number 14, it's asked in domestic electric circuits, the wiring with 15 ampere current rating is for the electrical devices. So 15 ampere current rating जो है वो किन डिवाइसेस के लिए होती है? तो 15 एम्पियर करंट रेटिंग उन डिवाइसेस के लिए होती है जो ज़्यादा करंट withdraw करते हैं, that is they have a higher power rating such as geyser. So option A is the correct answer. It's not for the lower power ratings such as fan. This is not the option. Metallic bodies and lower power ratings is not the option. Non-metallic bodies is not the option. So 15 ampere current rating is for electrical devices which have higher power ratings such as geysers and ACs and all other devices that withdraw higher current from the circuit. So our option is option A. Okay, for question number 15, in the following diagram, the position of the needle is shown on the scale of a voltmeter. So this is the calibrated scale of the voltmeter, and we have to find the least count of the voltmeter and the reading shown by it. So what is the least count? So least count is the reading shown by the one division of the scale. So what is the reading shown by the least count? So least count is the reading shown by the, so what is least count? Least count is the reading shown by one division on a calibrated scale. Okay. So here, if you see, so till here, the reading is 1.5 volt. So this is a voltmeter, so the reading is in 1.5 volt. And the number of divisions here are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that means for 10 divisions, 10 divisions is equal to 1.5 volt, and one division will be equal to 1.5 divided by 10, that is equal to 0.5 volt. So this is our least count. So least count is 1.5, 0.15 volt. Now, the reading, the needle is pointing here. This needle is pointing here. So the reading here would be for one division, it's 0.1, it's 0.15. So it's 1.5, and we have two divisions. So let's add 0.15 and 0.15, which will give us, so 5, 6, 7, and 8. This is 1.8. So that means the reading is 1.8 volt. So reading is equal to 1.8 volt. So least count is 0.15 volt and reading is 1.8 volts. So C is the correct option for this one. For next question, that is question number 16. Uh, we have to find out the resultant magnetic field at point P, which is situated midway between two parallel wires that are placed horizontally and each carrying a steady current I. So what would be the resultant magnetic field? Resultant magnetic field means the magnetic field due to this wire and the magnetic field due to this wire at point P. So first of all, let's consider this wire AB, and if we use the right hand thumb rule, let's find out the direction of the magnetic field in this case. So we know that around a straight carrying current wire, the magnetic field is in the form of the concentric circles. So here the magnetic field will be in the form of the concentric circle, and let this be the circle that passes through point P. And if we use the right hand thumb rule, which says that if we grasp the conductor in our right hand, the direction in which our finger curls, that will be the direction of the magnetic field. And if we consider this to be a plane of paper, so for this and use a right hand thumb rule, these magnetic fields will be coming out of the plane of the paper. So coming out of the plane of the paper means the direction will be like this. Similarly, for this wire, let's consider this is the magnetic field, that concentric circle that goes through point P. And similarly here, the magnetic field will be coming out of the plane of the paper. So at this point, these two, the magnetic fields will nullify. If you see, this magnetic field is coming out of the plane of the paper, and at this point, this is now going into the plane of the paper for this. So these two magnetic fields will nullify the effect of each other, and nullify means that they will cancel out each other, and hence the magnetic field at this point will be zero. So C0 is the correct answer for this one. Okay, for next question, which is the assertion and the reasoning based question. Assertion says that the strength of the magnetic field produced at the center of a current carrying circular coil increases on increasing the number of turns in it, which is true. Because let's say this is a current carrying circular coil. This is, let's say, attached to a battery here, and the current is flowing in this circular. Right, once again, this is a circular, let's say, coil, current carrying coil. It is attached to a battery. Let's say this is a battery here, positive, negative terminal. So negative and positive terminal here. Okay, now the current is flowing in this circular coil. Now, the magnetic field produced at the center of a current carrying circular coil. Now, the magnetic field produced by this current carrying circular coil will be in the form of the concentric circles for this part. Let's say these are the concentric circles. So, by the time it reaches the center of the circle, the magnetic field is almost straight. This is the magnetic field. And strength of the magnetic field produced at the center of a current carrying circle coil increases on increasing the number of turns. This is the magnetic field due to one turn of the coil. And if we increase the number of turns on this coil, let's say if we increase the number of turns in this coil, then the magnetic field will add up. Okay. The magnetic field here will coincide and that will keep on adding. So that means the assertion is true, which means that the strength of the magnetic field at the center of a current carrying circular coil increases because if we increase the number of turns due to the magnetic field at the center will be the sum of the magnetic field due to each turn. So magnetic field gets on adding up. So this is true. The current in each circular turn has the same direction and the magnetic field due to each turn then just adds up, which is also true. So current in each circular turn has the same direction and the magnetic field due to each turn then just adds up. So that means our option should be option A. Both A and assertion and reason are true. So for 20, it's A, option A. So this is also true. So current in each circular turn has the same direction, and because of which the magnetic field to each turn then just adds up, but it's not the correct explanation. So we can say both, or which is the correct explanation of it. So both A and R are true, and it's the correct explanation of A. So A is the correct answer for this one. Okay, for next question, that is question number 25. Which says a narrow beam XY of white light is passing through a glass prism as shown in the figure. And we have to trace it on your answer sheet and show the path of the emergent beam as observed on the screen PQ. So this is the screen. And we have to name the phenomenon observed and state its cause. So let's draw it on a sheet of paper. So this is the prism. This is white beam incident. Okay. And this is the incident ray. Now, had this prism not been there, the path of the ray should look like this. It should go in it may have gone in this direction, but because the refraction is happening in the prism, so it will bend into seven different colors, or it will split up into seven different colors. So for one color, this is the refraction and the splitting of seven colors. White light into seven colors is called dispersion. So it's 1, 2, 3, 4, 5, 6, and 7. And if this is a screen, so this will be the band of seven colors, which is called a spectrum. Okay. And the acronym used to remember the seven colors is WIBGYOR. So violet, indigo, blue, green, yellow, orange, and red. So this is the band of seven colors, which is called a spectrum. So this is how you will trace. This is the incident ray. So this is how we'll trace it your answer sheet and path of the emergent beam as observed on screen PQ. And let's also give the direction with the arrows. Okay. And this is the splitting of white light into seven colors, and this phenomenon is called dispersion. Okay, now what is asked in the question? Name the phenomenon. So phenomenon is dispersion, splitting of white light into seven colors. So this is splitting of white light into its constituent seven colors. Okay, now what is the cause? What is the cause of dispersion? And the cause of dispersion is that this light consists of seven colors, and seven colors bend at different angles. So different colors of light causes that the different colors of light they bend through different angles. So that is the cause of dispersion angles. And it's with respect to the incident. And this is because different colors have different wavelengths. Okay. So cause is that different colors of light they bend through different angles with respect to the incident ray because different colors have different wavelengths. This is the answer for the first part. Now, beginning with the or part, it is observed that power of an eye to see nearby objects as well as far objects diminishes with age. And we have to give reason for the above statement. The reason for the above statement is that with age, the defect that occurs in eye is because of the gradual weakening of the ciliary muscles and diminishing flexibility of the eyelids. So we have to give the reason. So give a reason for the above statement. Why the power of an eye to see nearby objects as well as far objects diminishes with age. And the reason is that it is, so this is all part, it is due to gradual weakening of ciliary muscles and with that diminishing flexibility of the eyelids. Okay, let me show you how. Let's say, let's suppose this is the eyeball. Okay, and here is the lens, which is held by the ciliary muscles. These are the ciliary muscles. So this is the lens, and these are the ciliary muscles. And we know that with age, these muscles will get weak. Now, the gradual weakening of the ciliary muscles, with this, there will be a lag in time to contract or relax the ciliary muscles, and hence the thickness and thinness of the lens will take more time, and this will reduce the flexibility of the eye lens, and hence we will not be able to see the far off and the nearby objects. So this is the gradual weakening of the ciliary muscles and diminishing flexibility of the eye lens. You need not have to draw this diagram. I just drawn it to I have just drawn it to explain you how the ciliary muscles are holding the lens. Now name the defect that is likely to rise in the eyes in such a condition. So the defect here is presbyopia. So you're not so presbyopia is the defect due to which you are not able to see the nearby and the far off objects because of the gradual weakening of muscles. So it's because of the gradual weakening of the muscles that myopia and hypermetropia occurs in your eyes. And we have to draw a label diagram to show the type of corrective lens. So the corrective lens used for correcting myopia is the bifocal lens. Okay, so for this we use bifocal lens. Bifocal means we have both concave and convex in that. So we have both concave plus convex in that. And for the bifocal lens, we don't have any ray diagram. It's used in the specs. Let's say this is the one part of the spec. And in the spec, there the upper part, okay, here. So let's say this is one part of the spec, and here the upper part, this one part. This part will have concave lens. So this is the concave lens, and concave lens is used to see for distant vision. This is for distant vision. And the lower part will have the convex lens. So lower part will have convex lens, and that is for the near vision. So we don't have an actual ray diagram, rather you will use one because it's a bifocal lens. So you will use uh, one part of the specs, and the upper part will have concave lens for distant vision, and the lower one will have convex lens for near vision for the near vision. So this is how you will draw a well-labeled diagram used for restoring the presbyopia of such an eye. With this, we are done with question number 25. Let's move on to next question. Okay, for question number 30, we have to complete the following ray diagram to show the formation of image. And let me complete the ray diagram in this case. So I'm going to redraw it. Okay, this is the cone. Let this be the center of curvature, and the midpoint is the let this be the center of curvature, and this be the principal focus. This should be the principal focus, and this distance is the focal length. This distance is the focal length. Okay, now the object is placed in front of the convex lens, and object is denoted by AB. Okay, and there is a ray that's going parallel to the principal axis. So this is the ray that's going parallel to the principal axis. Okay, and the ray that is going parallel to the principal axis will okay, and this ray will after reflection will go in this direction, and it will be it will be seems to be coming from the principal focus. So if it seems to be coming from the principal focus, then we have to draw a dotted line. So this ray will get deflected in this direction, and but to us it will seem to be coming from the focus. And this ray, we will have to draw one more ray to make sure that we have two rays intersecting so that we can get the image. Okay, so let's use this ray that is directed towards the center of curvature. So this ray is directed towards the center of curvature, and it will retrace its path, but to us it will seems to be coming from the center of curvature, and these two rays that we have assumed to be coming from the focus and the center of curvature will be intersecting at this point. So this is where the image is formed. So this is where the image is formed, and this is the image A dash B dash. So mention the nature, position, and size of the image formed in this case. So let's mention the nature of image. So its image is formed because we have assumed the rays to be intersecting behind the mirror. So this is virtual and erect. It's erect. So that's the nature of the image. Now, what is the position? Position is it's between the pole and the focus. So position of image is between pole and focus. So this is between pole and focus. Okay, this is the position. And what is the size? The size of the image is diminished because it's small in size, smaller in size than the object. So this is diminished. Okay, so this is the nature, position, and size of the image for part B, and A is this the ray diagram. So this is part B. Nature of the image is virtual and right position. It's between pole and focus, and the size is diminished. Let's move on to the third part. So position is behind the mirror. B between P and F. We can also write it's behind the mirror. Okay, so this is diminished. Okay, state the sign of the image distance. So this is the image distance which is denoted by B, and we know that the all the distances are measured to from the pole, which is the origin, and to the right, the distances are taken as positive. So image distance is positive because all the distances measured parallel to the incident ray from the pole to the right are taken as positive because this is the origin. And towards this the distances are positive, and towards the left from the pole the distances are negative. So image is formed here, image distance denoted by V. So image distance, that is V, that is V has positive sign. Okay, so this is the sign of the image distance in this case using this Cartesian sign convention. Let's move on to the next question. Okay, for next question, we have to give reasons for the following. And the for first question, it says the danger signals installed at airports or at the top of tall buildings are red in color because the red color is scattered least, and it's scattered least. So that means when you see them in fog or smoke, they can be easily seen from a distance because they are not scattered, and the red color remains at just one point. And this is because red color has high wavelength and the scattering is less. So answer for this is red color is least scattered by fog or smoke. So red color is, this is least scattered. And these are installed at airports and top of buildings so that we can see them from the distant far away place. So either you can write that red color is least scattered by the fog or smoke and can be easily seen from a distance. Okay, now this is because we can also write the red color. I will explain you how. The red color has high wavelength and therefore scattering is less. Is less. Okay, let me show you how you might had observed this in the prism, that when a white light passes through a prism, it splits up into seven constituent colors. So this is the white light, And when dispersion occurs, so these are the seven colors: one, two, three, four, five, six, and seven. And the first one is the red, and the last one is the violet. So this is the violet, this is the red. And if this ray of light was not going through the prism, would have gone, it would have gone like this. But now, so this is the original path of the incident ray. Now the red color has bent the least and the violet has bent most. So violet has the largest deviation, that means its wavelength is smaller, because red color has bent the least, its wavelength is the largest than the violet. So red color has high wavelength, thus its bend least and the scattering is less. So that's why red color is least scattered by fog or smoke and can be easily seen from a distance. So red color has high wavelength and the scattering is less. Now the sky appears dark to the passengers flying at high altitudes. Now let's suppose this is the Earth, and let's say this is the atmosphere, and we have air only in this region. Now let's say astronauts is viewing the sky from here. Now in between there is no air. So in between there is no air, so that means here scattering is not possible. So scattering is not possible. That means the particles of the air will not be able to scatter any of the colors, and hence for this the sky will appear black. So that's why the sky appears dark to the passengers flying at high altitudes, and for us it appears blue because we are viewing the earth from the surface and in between there is air, so here the scattering is happening. And very minute particles they scatter the color of the small wavelength, which is blue, because the size of the particles it matches with the wavelength of the blue color, and hence it scatters blue light. So what do you have to write here? The sky appears dark to the passengers flying at high altitudes. And answer for this should be there is no scattering of light due to lack of atmosphere at high altitude. So we will write there is no scattering of light due to, we can say, absence of atmosphere at high altitudes. So this is the reason for B. You don't have to draw this. This is just to explain. You don't have to draw this. This is the answer that you have to write, this one and this one. Okay, moving on to part C. The path of a beam of light passing through a collider solution is visible. So through the collider solution, the path of the light is visible because the particles of the collide are big enough. We know that the dependence of color, it depends on the size of the particles. Very minute particles they scatter color of smaller wavelength, and particles of collide are very big in size, and they are able to scatter all the colors. So it appears to us that it's a beam of light, white light. So that's why the path is visible to us. So particles of the collide are big to scatter the beam light, to scatter, this is the beam light, that is all the colors are scattered in same proportion and we see the path of the light. So the path of the beam light through collider solution is visible because the size of the particles of collide are big enough to scatter the beam light. So it depends on the size of the particles, the color. With this, we are done with question number 31. Let's move on to next question. So for our next question, that is question number 32, we have to state the rule used to find the force acting on a current carrying conductor placed in a magnetic field, and we know that it's a Fleming's left hand rule. So Fleming's left hand rule is used to find the direction of force acting on a conductor placed in a magnetic field, and we have to state that. So let's write down the Fleming's left hand rule. So this is Fleming's left hand rule. Now, what does it states? It states that if we stretch the forefinger, central finger, so if we stretch the forefinger, the central finger, and the thumb of your left hand of a left hand mutually perpendicular to each other. Now, such that, so you have to stretch the forefinger, the central finger, and the thumb of a left hand mutually perpendicular to each other, such that now if that means if your forefinger gives the direction of magnetic field, shows the direction of magnetic field, and central finger shows the direction of current. Okay, now then the direction in which the thumb points gives the direction of force. Then the direction of force or motion of conductor is given by the direction of thumb, is given in which the thumb points, or is given by the direction of thumb. Okay, so that means that let this be the forefinger, let these be the forefinger, the central finger, and the thumb. So this be the forefinger, which gives the direction of the magnetic field is noted by B, and this be the central finger of the left hand, which gives the direction of the current. Then this thumb, in which the direction with the thumb gives the direction of the force. So this is the Fleming's left hand rule. Okay, now let's move on to. Okay, for second question, given below are three diagrams showing entry of an electron in a magnetic field, we have to identify the case in which the force will be maximum and minimum, and give reason for your answer. So in this case, the electron is entering perpendicular. So the direction of electron, so the direction of electron is perpendicular to the direction of the magnetic field. So this is the direction of electron, then this is the direction of the current. Direction of the current is taken opposite to the direction of the electron. So that means that current and magnetic field are perpendicular to each other. So in first case, the force will be maximum because the current and the magnetic field, these are mutually perpendicular to each other. So these are mutually perpendicular to each other. We will write that in the first case, current, that is I, and a magnetic field which is noted by B, they are mutually perpendicular to each other. So direction of current is always taken opposite the direction of flow of electrons, and they are mutually perpendicular to each other. So here the so mutually perpendicular to each other means that the force in this case is minimum. Force will be maximum. So force here will be maximum. So this is maximum. Okay. So we have to give choose only the maximum and the minimum force. And so first case, the force is maximum because the current and the magnetic field are perpendicular to each other. Okay, in this case, the electron is moving in this direction, so this is the direction of the current, and the magnetic field is in this direction. So for the third one, they are parallel to each other. The force on an electron is minimum because the electron is moving along or parallel to the direction of the magnetic field. So here, so for this first figure, the this is second part. For the second part in first figure, that is in figure 1, the current and magnetic field are mutually perpendicular to each other, the force will be maximum. Now in the figure 3, the current and the magnetic field B are moving parallel to each other. So electron and magnetic field are moving parallel to each other, so that means the angle between them is 0. So that means the force will be minimum here. So these are the only cases. This is the figure third. So for figure third, the electron and the magnetic field are moving parallel to each other. So here the force is minimum. Here you will have some finite force because the electron is entering at some angle to the magnetic field. But we have to identify the case in which the force will be maximum and minimum. So this is the maximum and this is the minimum case. And here you will have some finite force. That is, you will have some get some value of the force acting on the conductor because electron is moving at certain angle with the magnetic field. So let's move on to the B part. We have to draw the pattern of magnetic field lines of a current carrying solenoid and a bar magnet and list two distinguishing features between the two fields. So this is the part B, and we know that what is a solenoid. So solenoid is insulated copper wire wrapped closely in the form of a cylinder. So let's first of all draw the pattern of magnetic fields around a current carrying solenoid. So solenoid is a current carrying insulated copper wire wrapped closely in the form of a cylinder. This is a cylinder. This is a solenoid. Now let's say this is attached. This is the key, and this is attached to some, let's say, battery to give the current. Now the current is flowing in this direction. Okay. But we have to draw the pattern of magnetic field lines in this case. So pattern of magnetic field lines will form closed loops. They will emerge from one end. Say, let's say these are emerging from this end. So this will be the North Pole and they are merging at this end. So this is the South Pole. So we will just draw only two magnetic field lines. So these are the pattern of the magnetic field line. Similarly here, the magnetic field line. Okay. And this would be another one. Okay. So the field lines are parallel. Magnetic field lines are parallel inside the solenoid. So just make sure that they are parallel. This is just a rough sketch. So make sure that you draw the parallel magnetic field lines. So magnetic field lines are merging at this end and they are emerging from this end. Okay, so this is the pattern of magnetic field lines. This is our solenoid and these are the magnetic field lines. And end where from where the magnetic field lines emerge. So here the magnetic field lines emerge. So this is the North Pole, and where the magnetic field lines merge, it becomes the South Pole. Okay, so this is the magnetic field lines of a current carrying solenoid. So we can label it as, make sure that inside the solenoid you draw the parallel lines. So this is a magnetic field lines of a solenoid. Okay, now we have to draw the pattern of magnetic field lines around a bar magnet. So let's say this is a bar magnet, and this is the North Pole, this is the South Pole, and so magnetic field lines will emerge from the north and will merge at the south. Emerge from south and will merge at this. Emerge from north and will merge at the south, north to south. Okay, so north to south. Let's give the directions. So these are coming at the south. Okay, so this is, let me draw a pole. Okay, this is a pattern of magnetic field lines of a bar magnet. So we can say that these are the okay, now let's move on to the next part. So list two distinguishing features between the two fields. So let me write down the two features, distinguishing features between the two fields. So this one is the magnetic field of a solenoid, and next is the magnetic field of a bar magnet. Okay, we have to list two differences. Now, so in this case, the magnetic field is produced by giving the current in this solenoid. So that means we can increase the magnetic field. The strength of the magnetic field can be changed by changing the current. So here we can say this is the difference is that here the strength of magnetic field that can be changed by changing the current. Okay, next. So this is the magnetic field of a solenoid, and this is the magnetic here. The strength of the magnetic field cannot be changed. Here the strength, because it's a natural magnet and its strength cannot be changed. So strength of magnetic field of a bar magnet, this cannot be changed. So this is the first noticeable difference. It cannot be changed. Now, what is the second difference? The second difference is we can also reverse the direction of magnetic field by changing the direction of it. So direction of magnetic field can be reversed by changing the direction of magnetic field. This can be reversed by changing the direction of current. So we can say that this is an artificial magnet. So here we can change the strength, we can change the direction. This is a natural magnet, natural bar magnet, where we cannot change the direction of magnetic field. The direction of magnetic field for a bar magnet cannot be changed. So here the direction cannot be changed. Okay, if you want to now write down the third difference, we can also write it down. This acts as a bar magnet as long as the current is flowing through it. So it is a temporary magnet. So we can say that it's a temporary magnet, and it is a permanent magnet. And the magnet, this is a magnet when current is flowing through this, so we can also call it an electromagnet. So it bar magnet is a permanent magnet, while the solenoid is a temporary magnet. So these are the three noticeable differences. Let's move on to the next question. For question number 36, part A, it's given that an electric iron consumes energy at a rate 880 watt when heating is at the maximum rate, and 330 watt of energy is consumed. That is when the heating is at the minimum. So the power is 1030 watt. So source voltage is 220. We have to calculate the current and resistance in each case. So let's find out the current and resistance in each case. And this is question A, part A. And that is when heating is at maximum rate. So when heating is at maximum rate. Now then, so when heating is at maximum rate, so power is 880 watt. So power is 880 watt, and source voltage is same. So V is 220 volt. We have to find the current and resistance in each case. That is, we have to find the current and we have to find the resistance in each case. So we know that P is equal to V into I. So power is 880 and potential difference is 220, and now current is 880 divided by 220, which is equal to 4 ampere. So current is 4 ampere. Let's find out the resistance. So resistance is equal to V upon I. So this is 220. Using the Ohm's law, we can find out the resistance. Resistance is V upon I. So uh, potential difference 220. Now current is 4. So this is 4 5s are 20. 4 5s are is 20, and resistance is 55 ohm. So resistance is 55 and current is 4 ampere in this case. So 4 ampere and 55 ohms is the resistance at maximum rate. Now let's find out move when heating is at minimum rate. So when heating is at minimum rate. So when heating is at minimum rate, what is the power? So power is given as 330 watt. So this is 330 watt and the potential difference is 220 volts. So let's use the same formula. We know that power is equal to potential difference into current. Power is 330, potential difference is 220, and we have to find the current. So I is equal to 330 divided by 22 and 3. So this is 1.5 ampere. Now we know that V is equal to IR. From here we can get resistance. So resistance is equal to V upon A. V is 220. This is 1.5. So resistance is equal to 2200 upon 15. 5 3s are is 15. 5 4s are 24 0. And now resistance is 440 by 3 ohms. So 440 by 3 ohms. So this is 440 by 3, which gives us 3 1s are is 3. 3 4s are 12. 3 6 are 18. 3 6 are 18. And 146.67 ohms. Okay, let's move on to the next part. What is the heating effect of electric current? So heating effect of electric current means that the when electric circuit is purely resistive, when let's say electric circuit is purely resistive. So when electric circuit is purely resistive, electrical energy is continually dissipated. So electrical energy is continually, we say continually dissipated. in the form of heat. So that means we have complete resistance in the circuit and all electric energy is converted into heat. So electric energy is continually dissipated in the form of heat, which is called heating effect of electrical. So condition here is that electric circuit is purely resistive and this is called heating effect of electric current, which is called heating effect of electric current. So this is what is heating effect of electric current. Now, okay, further is asked, find an expression for the amount of heat produced when it passes through a resistor for some time. This is Joule's law of heating. So the expression says that heat produced is directly proportional to the square of the current, directly proportional to the resistance and T. So this is the expression which is called Joule's law of heating. And remember, you will only be able to understand these things once you have studied the chapter. If you come directly to solving these questions, you may not understand the concept. To understand the concept, you have to thoroughly read your chapter, else you may not understand the concept behind this. So this is the Joule's law of heating. I have just given you the answers, what's written in the question. It's not the complete explanation or the concept of the chapter. So to understand the complete concept or to understand these questions completely, you will have to thoroughly go through the chapter itself. Let's move on to the next question. Okay, this is question number 39. And it's question number 39 is given that we hold a concave mirror in your hand and direct its reflecting surface towards the sun. So this is the concave mirror whose reflecting surface is curved inwards and direct the light reflected by the mirror onto a white cardboard held close to the mirror and move the cardboard back and forth gradually until you find a bright, sharp spot of light on the board, which is the image of the sun. So this spot of light is the image of the sun on the sheet of the paper, which is and the point at which we get the image of the sun is the principal focus of the concave mirror. Now, we have to list two applications of concave mirror. So, uh, uh, to give two applications of the concave mirror, we know the concave mirrors are used where you want to magnify or see something as a magnifying image. So it's used in torches to get parallel beams of light. So these are used in torches and in the searchlights that you might have seen above the walls installed on walls of the jail, the walls of the jail to throw a powerful beam of light, parallel powerful beam of light. So these are used in torches, these are used in searchlights, these are used in vehicle headlights. And all these vehicle and all these three cases, torches, searchlights, and vehicle headlights, they are used to throw a powerful parallel beam of light. And they are also used in shaving mirrors to closely see your face for shaving so that you can get a close shave. They are also used as dentist mirror to see the bigger image of the teeth or the cavities. They are also used in the solar furnaces to concentrate the sunlight and to raise the temperature of the furnace because the if you concentrate the sun rays the sun rays have infrared rays and that helps us in generating heat or raising the temperature of the furnace. So these you have to give any two applications. I have listed five or six here. You can give any two of these. So for part B, it's given that if the distance between the mirror and the principal focus is 15 centimeter, find the radius of curvature. So this distance between the mirror and the principal focus, mirror means the pole. So distance between the pole and the principal focus is the focal length. So this is a concave mirror, so its focal length is 15 and radius of curvature is the double of the focal length. So 2 into 15 is equal to 30 centimeter. I'm not using the sign convention. So the radius of curvature is 30 centimeter for the mirror. which is double of the focal length, and we have to draw a ray diagram to show the type of image formed when object is placed between pole and focus of a concave mirror. So let's draw a ray diagram, and this is a concave mirror. So let this be a concave mirror, let this be the pole. Okay, let me draw it once again. Let this be the pole of the concave mirror. This is the non-reflecting surface, and the reflecting surface is curved inwards. And let's move the pole. Let this be the principal axis that passing through the pole, and the center of curvature. Let this be the center of curvature. This be the principal focus. Now the object is placed between the pole and the focus. So we know we always denote the object and it's always upright. So arrow should be pointing upwards. This is the object. Okay, and this is the ray that is going parallel to the principal axis, and the ray parallel to the principal axis always after reflection always goes through the focus. Okay, this is all right. Now we have to consider one more ray. So let's say this is the ray. So let this be the ray that is incident obliquely on the principal focus. So it will follow the law of reflection and it will be reflected obliquely such that the angle of incidence is equal to the angle of reflection. This is the angle of incidence, this is the angle of reflection. Now these two rays are intersecting. Okay, this is, so these two rays are intersecting here. Uh, but let me not take this one. Okay, so this is one ray that is passing, this is incident obliquely on the pole. And let me take one ray such that let this be the ray. Okay, it is incident. This ray is incident here. Okay, let this be the ray that is incident. It's a angle. Okay, now let this ray be incident at 90° on the concave mirror. So this will retrace its path and will come back as it is. Okay, this be the ray. Okay, this ray goes like this, comes back, so it retraces its path. So it comes like this. Now, where will be the image form? Now, we have to extend these rays here. So, and let's mark them with a dotted line because these are not the actual rays. These are seems to be intersecting when produced backwards. So these seems to be intersecting here. So this is the point where these rays are intersecting, and this is the image formed, which is denoted by A dash B dash, and it's erect, so the arrow should be pointing upwards. So the image formed is virtual because it's not formed by the actual intersection of the rays. It's formed when we assume that the rays are intersecting when produced backwards. Okay, now, so this is the ray diagram. It was also only to draw the ray diagram and make sure that you give the direction for the rays because that will deduct half your marks if you're not showing the direction of the rays. So the ray diagram is drawn. Now, moving on to part C, an object 10 centimeter in size. So C part. So the object size is denoted by H and it's always upright. So height is 10 centimeter. Is placed at 10 centimeter in front of a concave mirror. So 10 centimeter is the object is denoted by U, and it's always negative because it's in front of the mirror, and all the distances are measured from the pole, and its distance is opposite to the direction of the incident ray. So this is negative 100 centimeter. If its image is formed at the same point where the object is located. So the image is formed at the same point where the object is located. So that means the image distance is also 100 centimeter. So image distance is also 100 centimeter. And because it's formed at the same point where the object is located, so it's also negative. Okay, now we have to find the focal length, and we are going to use the mirror formula. So using mirror formula. So mirror formula is 1 upon V plus 1 upon U is equal to 1 by F, which gives me 1 upon negative 100 plus 1 upon negative 100 is equal to 1 by F. So this is negative 100 and negative 100 is equal to 1 by F, which is minus 2 by 100 is equal to 1 by F. So F is equal to negative 100 by 2. So this is equal to negative 50 centimeters. So focal length is 50 centimeters. And negative indicates that it's the concave mirror. Okay. So what is the next part? Okay, we have find the focal length and now the magnification of the image formed with sine as per sine convention. So magnification of the image form. Now the magnification is given by negative V by U and it's negative for the formula. V is negative 100, this is negative 100 and magnification is negative 100. So, sorry, yes, magnification is negative 1. Negative 1, negative means that the image is, this is negative 100, sorry, negative 1. Sorry for that. This is negative 1. So magnification is negative 1. We have to find that in terms of, so 1 means that the image size is equal to object size, and negative means that the image is inverted. So negative indicates that image is inverted. So this is the case when the object distance and image distance are equal. Don't compare this case with this ray diagram. This ray diagram is when the object is between the center of curvature and the focus. And this is when the image and object are at the same distance. So here the focal length is 50 centimeter. That means that the image and the object are at the center of curvature. So negative sign indicates that image is inverted, and 1 means image size is equal to object size. Okay, with this, we are done with this section, this part, and with this paper code 3111 for 2023. Do like, share, subscribe. Thank you for watching.